Having done a particular example, the principle of superposition, I'd like to do now a much more general example. And this one is going to really help us understand a lot better the relationship between position and momentum in quantum mechanics, right? So, again, quantum principle of superposition makes us think that any quantum state, right? So which we now know we can describe by our wave function, and this quantum state, it could be, the state that we've been dealing with in our thought experiment, right? It had this normalization, 2 pi sigma squared to the 1/4 power, this Gaussian function with a 4 sigma squared on the bottom, and this particular phase factor e to the I k naught x, right? It could be this state, or in fact, we can just think about a generic quantum state, right? Characterized by a generic, arbitrarily valued wave function. The principle of quantum superposition says I should be able to write that state, right, as a superposition of pure states of any given observable, and I'm going to think about pure states of momentum. Now, momentum, you will notice, is a continuous variable. So this is going to be sum over a continuous pure states of momentum. Now, of course, because momentum is a continuous variable, I have to integrate over all values of momentum. And once again, I'm just using the fact that wave vector k is essentially the same thing as momentum, right? It's just a different label and measured in different units converted by h bar. So I would think I should be able to write any state as a superposition of the pure momentum states that I would get if I were to measure the momentum. Now, it's supposed to be a superposition of those states. So when I look at the generic quantum principle of superposition here, right, it's going to be a sum. Now it's an integral because I'm doing a continuous system. Here I'm supposed to put the pure states with respect to my observable of the corresponding values that I'm summing over. And we did just decide, really, that what de Broglie really meant was that these e to the I kx factors are our pure states of momentum. So this would be e to the I kx. And what that represents is a pure state of momentum p. And of course, the value of p is going to be h bar times k. And the last piece of the quantum principle superposition is that there have to be some weight factors in here. And those weights I will call psi of k, but it's a different function, and it's a function associated with momentum, so I'm going to put a tilde on top of it, right? And these are just my weights. If you feel more comfortable, you can think of these as just being w of k. Right? It's just some function of k. It's some set of weights that just depend upon k. I'm just giving it a suggestive name because I know it's somehow related to my wave function as a function of position. So this is a pretty strong mathematical claim. Right? We've come to it by general physical principles, which is what's beautiful about this. It's all buried in the de Broglie hypothesis. But what it's saying is that I believe that any function, arbitrary function psi of x, can be written as an integral in this form with some particular weights. Now, this particular form of integral, right, has a name, and this is the Fourier transform. This is at least, right, this is the Fourier transform. Now, to save writing on the board, I sometimes like to write this symbolically. So what this is saying is if I want to get psi of x, right, I can start with this other function, which is a function of these weights, and I do this mathematical procedure to it in order to get back my function of position. That mathematical procedure, this integral and multiplication, is called the Fourier transform. I like to give it a special symbol. I call it script f, and it would look something like so. But that's just, just a terminology and a little bit of notation. I'm really talking about this type of integral. Now, this right now is a pretty strong mathematical claim that for any function that would represent a wave function, I can write it as a superposition like this with some weights. This requires some kind of proof. And there are two general ways to prove something, right? And the best way, rather than an existence proof, is a proof by construction. In a proof by construction, it's much more useful because in a proof by construction, we actually are going to figure out what weights we should put in here to make sure we get any given function that we want. So that is really the question, right? We're going to guess at what form I should put for this psi tilde of k. Right? I'm going to guess it has some particular form, and we'll be able to prove that this statement is true if we take our guess for psi, insert it into this integral, and integrate and get psi of x back again. Right? That's how we're going to prove that this is possible. And at the same time, that will teach us what these psi tilde k's actually are. Now, but to do this, we need to be able to make some kind of guess for these. But this, again, is where Dirac and de Broglie come in. These psi tilde of k represent the weights in my quantum superposition of my pure states, right? So I'm going to guess at, right, the idea then that the probabilities of measuring different values of k, right, has to be related somehow to these weights, these psi tilde of k. And I'm looking for some kind of inspiration for what psi tilde of k is. But given, right, that these weights have to be related to my wave function, gives me some pretty strong hints as to what this psi tilde of k must be. So let's take a look at what the momentum distribution actually is, and then we can get a sense for how we can determine what the associated weights would be. Now, we actually had, way back at the beginning of our thought experiment, an expression that told us that probability. Here it is, right? To get the probability in k, I have to do this nasty integral of psi times e to the minus I kx, right? And to actually get the probability, I then take the magnitude of that and I square it. So I know then this probability is somehow related to, I know that probability is actually proportional to the integral over x of psi of x times e to the minus I kx quantity squared. And that integral has to be somehow related to my psi tilde. So one guess might be, well, maybe psi tilde actually is my probability, and then it could be my probability, right? And then I would just insert this for my guess. But that doesn't seem quite right, right? Firstly, that would give a very complicated expression that we'd have to integrate, and we want to avoid that if possible. But secondly, we've been getting these inklings that the probability of the value of an observable should be related to the magnitude squared of the weight, right? That was this kind of guess we were building at. So maybe, right, P more goes like the magnitude of psi tilde squared, right? Which would then mean, because I know it's actually proportional to this quantity, that would mean psi tilde, a very good guess for psi tilde would be this. So we're going to guess it has this particular value, the integral of psi of x times e to the minus I kx. And if we are right, we've figured out how to undo this Fourier transform and to get our psi k back again. So this is really a guess still of what is known as the inverse Fourier transform theorem. And it's really remarkable that we can, if this works, that we can guess at something as profound as that mathematical theorem simply by employing this very powerful statement about the world, our principle of quantum superposition. So what we're going to take up next then is what happens when I insert this guess expression in for psi tilde of k, and I want to see if I can get back my psi of x. And that's what we will be talking about next.